Hey everybody. My name is David. I'm here to speak about reverse engineering and Pwning. I'm a security researcher at Synac. I love listening to metal, playing capture the flag, snowboarding, skateboarding. I'm your average millennial. I love the Pacific Northwest. That's my home. I live in San Francisco. I graduated from the Evergreen State College there, where my interest in Pwning was sparked. I used to play with a CTF team called the Ganui Ducks. And I'm still learning. But seriously, if you guys have any sort of feedback or questions, like my host said, please feel free to share with me, and we can improve the end result of this talk together. In general, the motivation for reversing and Pwning is cash. There's a lot of money to be made. When something's difficult, it can feel rewarding to overcome obstacles and defeat challenges. So for a lot of people, it's just the pure challenge of it that makes all of this worth it. I listed a lot of the more beginner-oriented bug bounties and associated average payouts. And I work at Synac. Synac runs a great bug bounty where people like yourselves can make money and use skills related to the ones that you'll learn in this talk in our mobile application bounty. Assembly may be a review for some of you, but we'll briefly introduce it to ensure that all of us are on the same page. My hope is that practical examples will keep interest fresh throughout the talk for everyone, no matter what your skill level is. So let's have a round of questions. You guys can respond with thumbs up or thumbs down. Who's seen a debugger before? Sweet. Who's written a line of assembly? Awesome. All right. Nice. So we're going to talk about bugs and techniques for studying programs on disk and in memory. And hopefully I'll have time to show you guys a Pwn challenge at the end. So let's start off with a demo. Okay. Got this program. It's got two structs. They just represent various kinds of bears. So we've got a polar bear and a grizzly bear. Notice that the polar bear has this field it's a function pointer. We've got a secret admin shell, an edit polar bear function, two printing functions for each kind of bear. And here's our menu. This is a simple menu-driven program. You can make a grizzly or a polar bear, delete your bear, print your bear. You can edit polar bears, and you can exit. And then we've got our main loop here, which accepts whichever option you want and then acts on it. The bear creation option allows you to rename your bear if you already have one that exists, and allows you to create bears. It uses malloc over here to allocate space for the bear and then prints the address of it. And then it just accepts the various fields. And you've got the same thing for grizzly. And we've got our deletion options here, which just free the memory for either bear. And you can print your bear. Notice that the print option for the polar bear uses the function pointer that we saw earlier. And then you can edit and exit. So I've got a few questions for you guys. Again, you can respond with thumbs up or thumbs down. So if a function isn't called in the main program, like we saw that the secret admin shell function is never referenced in the program, does it get compiled into the binary or not? Thumbs up for yes, thumbs up, down for no. All right, cool. It looks like we have people here who have seen this kind of thing before. Are the grizzly and polar bear structs allocated next to each other in memory? Okay. And can the grizzly, if you delete a grizzly bear after making one, can you print it afterwards? It's really cruddily written, isn't it? So we'll answer these questions formally throughout the talk. So let's take a look at low-level programming fundamentals for the 32-bit x86 CPU. So a CPU is composed of a collection of registers. You can imagine a collection of registers as a reusable feeder sign. Notice that over here we've got the list of movies, and over here we've got this running message that just talks about small business. In the same way, our register illustration points out that these registers over here are general purpose registers, and then down here we've got pointers. The other thing of note is that you can reference subsections of your CPU by different aliases. So like AX registers the lower, references the lower 16 bits, and then so on and so forth for the other labels. So assembly is about as low level as programming can get. Technically, you can program in machine code, but that wouldn't really be any fun for anyone. And assembly languages are sets of instructions that can take operands, which can be registers or constant values. Instructions are simple logical, arithmetic, or state modifying operations. Notice below we have this move instruction, which just moves the constant 5 into the AEX register. And let's take a closer look at this illustration of the compiled square function. So it's color coordinated, which is really nice. This declaration relates to the function prolog, which just saves the stack frame for the caller and then allocates or creates a new stack frame for the body of this square function. Then we've got the meat of the function, which just multiplies its argument by itself. So this instruction takes the argument and puts it into EAX, and then this instruction takes EAX and multiplies it by the argument again and stores the result into EAX. And then we restore the caller stack frame and return control of the CPU to the caller. So we've seen in general how code is represented at a low level, but what does a process look like at runtime in memory? I'm sure most of you have heard others talk about the heap and the stack. These are two regions that most variable data is stored in. Heap is for variable sized data, and the stack is primarily for local variables and function arguments whose size is known at compile time. This memory layout illustration is extremely simplified. There are segments of memory that aren't shown here for brevity. Row data is known as read-only data. It's used for immutable values, thus read-only. The data segment is used for initialized global variables. So the stack frame holds the function metadata and local variables. When a function is called, the caller has to pass along arguments to and a pointer to the instruction following the function call so that control can be returned back to the caller. The callee has to save the caller stack frame and then allocate space on the stack for local variables. Notice that arguments get pushed on right to left. So argument 2 gets pushed on first, and then argument 1 gets pushed on. Then the caller can save its return address, and the callee can save the stack frame for the caller. And then local variables are pushed on top down. So var1 gets pushed on first, and then var2 gets pushed on. So now that we have the basics down for looking at assembly, let's try our hand at a simple crackme. So on the left here, I'm interacting with this reverse me binary, and then on the right, I've got a disassembler open. This is called Radare, and it will look a little unfamiliar at first, and I'll introduce pieces of it, and it'll start to become a little more familiar as I move along. So let's just try entering some garbage data into this binary, and we see that obviously that failed. But what we can do with this is we can take this failure string and see in the binary where it's referenced in the code and start to figure out how it's working internally and see what is the correct data. So I'll just search through the strings in the binary for fail. Is this viewable for everyone? Probably not, huh? You guys want me to make it bigger? All right. Is that a little better? Cool. All right. So we see that the failure string has this has an address right here. This is the address of the failure string. So we can take that address and we can cross-reference it with the code. And we see that it's used in the main function and in this sim.isAWinner function. So first, let's take a look at where it's used in main. So we'll seek to main, and then we'll print out the disassembly. And it's a little much, but we can scroll up to the top and see what's going on. So we start to see things of interest. Look, this is fgets, which is receiving our input, and printf over here. Unfortunately, it's going off the end of the screen, but you can see here it says enter an input. So that's our first input prompt. And as we learned that arguments are pushed on right to left, unfortunately it's going off the screen, but Radar gives us this really nice function prototype for fgets, and it shows us the prototype. So on the rightmost, we have the file pointer for the stream that we're getting input from, and then we've got the size of the input, and then S, which is the destination buffer. So this EAX at the top pushed on, this is the file pointer, and then hex A, that's the size, and then local 20 hex, that's where our first input is. So we can take that and remember that as we continue to reverse. Here's our second input, which is stored in local 16 hex. And then we've got this call to strt_along, which just takes local 20 hex and converts it to an integer. We can tell that it's an integer, or a decimal rather, because hex A is 10. And so that's the base that strt_along is using. Anyway, the output is taken and compared against this hex 539. The return value for every function can be expected to be in the EAX register. For those of you that can't see, this is the EAX register. It's compared with hex 539, which is, in decimal is 1337. So that's our first correct input. We know that. Then sim.isAWinner is called if that comparison passes. So we can seek to sim.isAWinner and see what's going on there. So all that happens here is that strcomp compares two strings. Radar is being nice to us again and showing us the string that's referenced 23EA5 is our second correct input. So I can go back over to where we're interacting with the binary and then run it again. For our first input, it's 1337, and our second input is 23EA5. And we get you win instead of fail. Awesome. So what did we learn? We learned that string cross-references are incredibly useful for finding related code to whatever prompt it is that we're seeing. Return values are always in EAX, and the order of arguments are pushed onto the stack from right to left. Having done some simple reversing, let's try our hand at some Pwning. I'll introduce some examples here. All of these will be available as examples to you guys afterwards. So Stack Overflows are mostly dead now, but they're still worth mentioning. In this example, an out-of-bounds write allows the user to write to a local variable. What you should see here is that hex 10 is the amount of input that's allowed from fgets, and then we've only allocated 10 bytes in the buffer. So because arguments are pushed on top-down, we're allowed to write to I. Format string bugs exist where programmers allow the user to specify the format string that printf or one of its sibling functions take. They allow one to read information from the stack or write to it with the %n modifier. In this example shown here, notice that I'm reading data off the stack in hex encoding with the %x modifier. So as my buffer, I just enter in the format string because my input's passed directly to printf, and I get raw data off the stack. In this example, I'm showing a trick called direct parameter access. So I noticed that the third piece of data that I got off the stack started in 8048, which is in the code segment. As you practice, you'll start to see that. And so I can access that directly since it's the third piece of data that I got off the stack, I can just provide 3 as the direct parameter. Wild copies are an increasingly common bug class now. They exist when a programmer doesn't account for cases allowing an attacker limited control over the size of a copy, or when the programmer simply allows a copy large enough to cause a fault. Yeah, this example will be available to you guys afterwards. Use after freeze exists where programmers forget to set references to allocated data to null, as you guys pointed out earlier, after freeing them, allowing references to be reused. In conjunction with this, it's worth mentioning how malloc organizes allocations on the heap. The malloc algorithm used in this particular brand of Linux shown here illustrates this. So allocations are organized according to size. There's like, you can imagine bins, like there's very small, small, medium, large, huge. So in this example, I allocate 20 bytes, and then I free it and allocate 15 bytes and free it. And over here, you see that the same address is reused to allocate those 2 pieces of data. So the community is booming with new tools in the area of binary analysis. There's a lot of tools, but showing here some of the most popular ones. On the left is IDA. This is like a premier static analysis tool. It's awesome because it's got a really great decompiler. It's the industry standard for analyzing disassembly. On the right, this is Voltron, which is it's a GDB init. You can think of it as like kind of a visual front end to GDB. You can organize panes. So there's a breakpoints pane, there's a backtrace pane, and registers. Pwn tools is generally used for connecting to and interacting with remote services, but it's useful for so many purposes surrounding the process of exploit development. In the screenshot, the user is testing some shellcode and interacting with it. Notice at the bottom, there's the result of ID, which shows that we're the zero cool user. And here's the command ID. Checksec is a helpful tool for showing which exploitation mitigations are enabled in a given binary. So notice that the NX is enabled on this binary. So basically, all the data segments are marked not executable. So stack, heap, data segment. So what now? Well, I provided some challenges and a vagrant box for you guys to play with. Take a picture of this slide if you guys want to play around with some of the examples that I showed. And in return for write-ups on these challenges and a few extras that I've thrown in there, I'm giving out books. If you guys send me a good write-up that I can tell wasn't just copied off the internet, I'll gladly reward you guys with a book. Yeah, there's extra pwnables too that I haven't shown in my slides. You guys want me to go back? Sorry. All right, and I'll make the slides available afterwards too. So how about bypassing mitigations? Want to be there, right? So let's try a pwn challenge. So we're going to go back to this bears example. Get control of my mouse. OK. So I'm interacting with the binary in this pane. Basically, I've made a binary, and it printed out its address. Just remember, it ends in E008. Here, I'll make it bigger for you guys in the back. Oh, wow. This is on my screen. Jeez. So sorry, y'all. Better? OK. All right. So we made a grizzly bear, and then now it's waiting for us to do something else. So how about let's try one of the questions I asked you guys was, can we delete it and then reference it again? Just for those of you who don't believe me, let's delete our grizzly and then print it. So printing still worked. We got 5 months, or one month hibernated, rather. So what happens if we create a polar bear in its place? So that same address ending in 008 was assigned to our polar bear that we just made. Now, if we fill in the fields and then do our grizzly print again, what happens? Well, we get this really crazy big number of months hibernated. So what do you guys think that is? Here's a hint. So the months hibernated is 20 bytes into the struct. You see that? 16 and 4. And see what's at that same location for the polar bear? It's the function pointer. So we just leaked memory. We now know where the function is in memory. So how can we use that? Well, the offset between the print polar bear function and our secret admin shell function always stays the same. So if we just know the difference in those two locations in memory, then we can calculate the location of the secret admin shell in memory as well. And then we can create a new grizzly with that address of the secret admin shell function as its hibernation, as the number of months hibernated, and then we can refer to that grizzly as a polar bear, since those references can get mixed, right? If we delete a polar bear and then allocate a grizzly in its place, then that reference to the polar bear still exists. If we print our polar bear after that, it'll use the address that we've provided it. So let me try this out. So if I make a new polar bear, and then fill in the fields really quick, delete it, make a grizzly in its place, and then fill in the fields. So it's asking for the number of months hibernated. We just need to take that number that we leaked out, calculate the difference, which I'll do over here. That is the address of our secret admin shell. So now if I print that polar bear, I should get a shell. Thanks. All right. So we pwned it. By the way, there's another bug in that binary, so there's something left for you guys. So here's some super helpful resources that have helped me in learning. Ginville is a Dragon Sector team member, one of the best CTF teams in the world. He does like write-ups and for like CTFs of all skill levels, it's super helpful. Live Overflow is pretty similar. Something I thought that was really cool is the guy who does Live Overflow went over the new Nintendo Switch bug, the arbitrary code exec. So that was like really fun to watch. RPISec MBE is where I learned most of this stuff. It's a free online class that teaches binary exploitation. It's incredibly awesome. Challenges.re and pwnable.tw if you just want more reversing and pwning challenges. A bug hunter's diary, if you guys are interested in actually like making a bug hunting career out of binary exploitation, I highly recommend this book. Walks through everything. And that's all the time I have. Thanks to everyone whose work I ripped off. Just kidding. It's the only inspiration. Thanks especially to Richard Weiss and Mike Pizza, Sinak, Rico Butts, my mentor, who is definitely bored with my talk by now.